Hello friends, in today's video, I'm going to present to you 10 selected test items, okay, on the topic Newton's three laws of motion. So these questions are all conceptual. Nothing is quantitative. So we just look at how the three laws of Newton, the first law, the second law, and the third law, no, are applied in explaining certain situations. So hang on, we're going to start now with question number 1. When an object has no acceleration, we can conclude that letter A, no forces are acting on the body. Letter B, it is at rest. Letter C, the net force must be equal to 0. And letter D, it is moving with constant velocity. Alright? Which of this is the best answer? If your answer is letter C, then you are correct. To explain why the answer in question number 1 is letter C, okay, we have here a diagram that explains these 4 concepts governed by the first law of motion. Alright? So in the problem, we were told that the body has 0 acceleration. And our answer was that the reason why a body is or has no acceleration is that the net force acting on it must be equal to 0. Alright? We did not accept the other answers. For example, we cannot say that just because the acceleration is 0, it doesn't follow that the body is at rest. We are not sure yet because acceleration equals 0 can mean two different things. It can mean the body is at rest or the body is moving with constant velocity. Alright? So, only between acceleration equals 0 and F net equals 0 that we can see here a double way arrow to show that when a body is or has no acceleration, it's simply because the F net is 0. Or we can also say that a body with no net force, okay, also means that the body has no acceleration. But in the case of a body without any speed or a body that is at rest, the only thing that we can conclude immediately is that because there is no net force, all right, or because the acceleration is 0. Now, in the case of a body with constant velocity, all right, it is because there is no net force. And constant velocity can also mean that the acceleration is 0. So between at rest here and uh, having an acceleration equals 0, we do not have a two-way arrow. It's just from at rest going to a equals 0. Likewise, for constant velocity, we only have here a one-way arrow. No, all right. I hope the explanation for question number 1 is clear. Question number 2. If the mass of a sledding block is tripled while a constant net force is applied, then its acceleration, letter A, increases 3 times. Letter B decreases by 1/3. That means 1/3 of the original. Or letter C remains unchanged. Or letter D decreases by 1/3 16. So, this question actually is an application of Newton's law of acceleration. And if you recall, the mass of a body is inversely proportional to the acceleration when the net force is held constant. So it says there that if the mass of the sliding block is tripled, what will happen to the acceleration? The fact that they are inversely proportional. So if your answer is letter B, then you are correct. In question number 3, in which situation is the action-reaction pair of forces present? So obviously, this is related to Newton's third law, which is the law of interaction. So we have here three situations. Letter A, stalled car at the corner of the street. Is there action-reaction pair of forces here? Or is it letter B, a huge boulder rolling on a hill? So when a boulder is rolling on a hill, is there also an action-reaction pair of forces existing here in this situation? Or is it letter C, a skydiver descending from an aircraft? All right. So this diver could probably be descending with constant speed, or he must be accelerating. All right. So it's not specified. But our action-reaction pairs of forces exist in letter C. So if your answer is letter D, then you are right. Why is action-reaction pair of forces present in each of the three given choices in our preceding question? All right. So when a car is stalled, that means that the body or the car is at rest. And we know that two vertical forces must be acting on the stalled car. We have the force exerted by the road on the car, and that is directed upward. Okay? Then consider this as the action force. Then of course, an equal but opposite force, we call it the force exerted by the car on the road, also exists. Okay? So these are what we call action-reaction pairs. This is for a body that is at rest. Now how about when a body is, supposing the skydiver is accelerating downward? All right? We know that the diver is being pulled by gravity, or the force of the earth on the skydiver that is directed downward. If that is the action force, then what is the reaction force? Of course, if you notice the way we label the force, for example, the force of the earth on the skydiver is labeled here as F sub ES. Okay? So the first letter, the first subscript refers to the body that is exerting the force, and then followed by the body where the force is being exerted. FES, force of the earth on the skydiver. Okay, how do we represent the reaction force to that? Okay, it is represented here as force FSE, meaning the force exerted by the skydiver on the earth. and that is, of course, directed upward. So you will notice that the force where it is being acted upon, okay, is not the same. For example, for the action force FES, the last letter in the subscript is S, referring to the skydiver, and the reaction to that FSE, the second subscript is letter E, meaning the Earth. All right, that is one of the characteristics of action-reaction forces. If you remember, okay, the two forces may be equal and opposite. They are acting at the same time, but they are actually acting on two different bodies. All right? So this is known as the law of interaction. And it doesn't matter if the body is not moving. Okay? It may be moving, it may be at rest when it is in motion, okay, with constant velocity, or if the body is accelerating, the law of interaction or the action-reaction pair forces always, they are always present. Okay, question number 4. If a mass of 1 kilogram is accelerated 1 meter per second squared by a force of 1 newton, this is understood to be the net force. What would be the acceleration in meters per second squared of a 2 kilogram mass acted on by a force of 2 newtons? Is it letter A, increases 3 times, B, decreases by 1/3, letter C, remains unchanged, or letter D, decreases by 1/16? So we are looking here for a possible change in acceleration. So in case 1, we are given that the mass is 1 kilogram, and this is acted upon by a net force of 1 newton. What would be the corresponding acceleration? All right, so here is a quick computation. There you are. We just divide the net force by the mass. 1 newton divided by 1 kilogram, and the resulting acceleration is 1 meter per second squared. Now, what if, says there, what would be the acceleration of twice the mass? That means of a mass 2 kilogram, which is acted upon by twice the force, 2 newtons. What would be uh, the acceleration? Will it be different? Okay, so again, we do a quick computation, and we get here for the F net 2 newtons divided by the mass 2 kilograms, and the acceleration is 1 meter per second squared. So there is no difference in the acceleration for the two cases. That is why our answer is letter C. All right, for this question, we are given a guava that is at rest, lying at rest on your palm. Question is, which of the following forces is an action-reaction pair existing? All right, so letter A, the force of guava on your hand and the force of your hand on the guava, okay? Or is it letter B, the force of the earth on the guava and the force of the guava on your hand, okay? Labeled here as FEG equals FGH. For letter C, we have the force of your hand on the guava and the force of the earth on the guava, labeled FHG being equal to FEG. And the last choice, letter D, the force of the earth on your hand and the force of your hand on the guava, labeled as FEH, being equal to FHG. Alright, so what do you think is our correct answer? Notice that the two forces mentioned in each option are labeled here, and this is what you are supposed to look at carefully, examine them carefully, the way we label each action and reaction forces. So look, we said earlier in one of the questions we tackled earlier, to find out if the two forces given are action-reaction, all you have to do is examine the subscript. For example, for the first one, force of guava on your hand. Okay? Is the reaction of that force, or should the reaction of that force be labeled as FHG? Notice what happens to the subscript. Alright? GHHG. That's for option letter A. Now for option letter B, the force of the earth on the guava labeled as FEG, and the force of the guava on your hand labeled FGH. Okay? Do you notice something? Alright? FEG is no longer the reversed subscript of FGH. In other words, the two forces mentioned in letter B, okay, doesn't involve just two bodies interacting, but there is already, okay, there is already a third body involved, and that is the hand. E stands for the earth, G for the guava, and then H there is for your hand. Okay, action-reaction only involves two interacting bodies. So it looks like that letter B cannot be a possible answer. Let's look at letter C. Okay? The action force FHG and the reaction force FEG. So, is the subscript of the action force the reverse of the subscript of the reaction force? Of course not. Okay? It involves three bodies already: the hand, the guava, and the earth. So just like in letter B, option letter C cannot be correct. Let's look at the final choice. Force of the earth on your hand, FEH, and force of your hand on the guava, FHG. Again, you will notice that the subscript of the action force is not the reverse subscript of the reaction force, meaning, again, three bodies are already being labeled here: the earth, the hand, and the guava. In short, our best answer for this question must be letter A. Question number 6. Compared to the force that the sun exerts on the earth, the force exerted by the earth on the sun is: letter A, greater; letter B, less; letter C, equal; or letter D, negligible. Alright, so first, let us first label the forces involved here. The force that the sun exerts on the earth, as well as the force exerted by the earth on the sun. Right? So this force, which is represented by a vector arrow, notice that the tail of the arrow is attached to the earth, meaning this is a force that is exerted on the earth. Okay? And look at the way we represent the force, F sub SE. S stands for the sun, E, earth. Okay, so this is the pulling force or the attractive force exerted by the sun to the earth. Okay, now the other force is the blue vector arrow. Notice that the tail of that vector arrow is attached to the sun, and we label it as F sub ES, meaning the force exerted by the earth on the sun. All right, force of the earth on the sun, and then here we have force of the sun on the earth. All right, so what kind of forces are we talking about here in question number 6? Okay, the two forces are supposed to be opposite, right? As shown in the diagram. Okay, another thing, they are acting on two different bodies. Okay, now the question is, how would you compare the magnitude of the two forces? It looks like that these two forces are actually action, reaction, pair of forces. As you may notice, the way we represent each force, the way they are labeled, FES, this is the pulling force of the earth on the sun, and if that is the action force, the reaction is FSE, meaning the force exerted by the sun on the earth. Alright? In short, the two forces mentioned in this question are just but action, reaction, pair of forces. In short, alright, our best answer for number 6 is that the two forces are in fact always equal. We are now in question number 7. A ball sits at rest on a horizontal tabletop. Which of the following statements explains why the ball stays at rest? Alright, so the keywords here are staying at rest. So the ball is staying at rest, right? And if we are to identify the forces acting on the ball, alright, then we will have the downward force that the force of gravity exerts on the ball. That is represented here by the force F sub GB. Again, this is the force exerted by gravity of the earth exerted on the ball. Sometimes we also call this the weight of the ball. Now, what's the other force exerted on the ball? We have an upward force that is exerted by T. T is the table, all right? Force exerted by the table on the ball. Sometimes we also call this the normal force. As you may have remember, when you say normal force, that is the force exerted by any surface on a body that is attached to the surface. The vertical force exerted by a surface on an object lying on such surface. But in here, we label it as FTB. Now, notice that the two forces, the way they are labeled, okay, let's look at the downward force, FGB, force of gravity on the ball. Then the reaction force, the other force, the upward force, FTB. All right? Could these two forces be considered action-reaction? The answer is no. They are not action-reaction. Okay? So when we examine the subscript, notice that this one is the force exerted by the table on the ball, and the other one is the downward force exerted by the Earth's gravity on the ball, notice that the second letter in the subscript is the same. Okay, subscript B, subscript B. So we're talking about the two forces being acted upon the same body, which is the ball. So they cannot be considered as action, reaction. All right? Now, this statement in number 7 is actually explained better not by the third law or action reaction, but this is in fact well explained by Newton's first law of motion, the law of inertia. And what does the law state? States that whenever a body is at rest, it is because it is acted upon by zero net force. All right? A while ago, there was an example where we were talking about uh, the law of inertia, where F net is equal to 0. In short, these two forces that we have just identified are equal in magnitude. They're opposite in directions. One is downward, the other is upward. But they're acting on the same body. All right, so that is how we analyze the vector diagram here. All right, so looking at the following statements, which do you think best explains why this ball stays at rest? Why the ball stays at rest while on top of the table? Here are the four explanations given. First, is it because the force of gravity on the ball is balanced by the normal force? In short, is FGB equal to FTB? Okay? Now, take note that the two forces being equated here has the subscript. The second letter of the subscript is the same, B and B. This means these two forces are acting on the same body, which is the ball. Now, how about explanation in letter B? The upward force that the tabletop exerts on the ball is equal and opposite to the downward force of the ball on the table. The two forces are labeled FTB and FBT. Notice that the subscript of the first force, FTB, alright, is just the reverse of the subscript of the other force, FBT. So what does this remind you? These two forces are in fact action, reaction. Okay? Now let's look at the explanation given in letter C. The upward force that the ball exerts on the earth is balanced by the force of gravity on the ball. And these are labeled as FBG and FGB. Okay? The force that the ball exerts on the earth. So this is exerted on the earth by the ball. And the other force is the force exerted by gravity on the ball. Again, notice that the subscript, okay, of the two forces are just opposite to each other. So these are also considered action-reaction pair. And the last explanation given in letter D, the downward force that the ball exerts on the tabletop is balanced by the force of gravity on the ball. The two forces are labeled as FBT and FGB. So examining the subscript, FBT, FGB. Alright? So are these action-reaction? Of course they are not. Are these two forces acting on the same body? No. because look at the second letter in the subscript, T, B, meaning this one is table, the other one is the ball. All right. So what do you think is the best answer? Okay. The best answer, of course, is letter A. Now, okay. Uh, you will notice that in the given problem, as I mentioned earlier, the only law, Newton's, among the three laws of Newton, it is the first law, the law of inertia, or where the F net equals 0, that will explain, all right? The first law is the only law that explains why a body stays at rest or why a body moves with constant velocity, okay? We do not use the third law, the law of interaction, to explain why a body stays in equilibrium, all right? It is the first law, the law of inertia, that should explain why a body stays in equilibrium. That is the reason why our answer is letter A. Okay, we now have question number 8. You push a stalled car with a horizontal force F of 275 newtons. The car does not move. What frictional force, small letter f, is acting on the car while you are pushing it? Alright, so as shown in the drawing, we have there a man trying to move the car, probably has been stalled. Okay, so the arrow is the force that the man exerts on the car, labeled here as capital F. Then we also have the force that is exerted by friction. This force of friction is exerted on the car, specifically on the wheels of the tire of the car. Now, uh, the question is asking us to determine the amount of force of friction when the applied force, okay, capital F, is given at 275 newtons. So, the other condition specified here is that the car does not move. Okay, so in spite of the fact that there is an applied force of 275 newtons exerted by the man trying to push the stalled vehicle, okay, there is no motion as far as the car is concerned. So, what do you think is the frictional force acting on the car while you are doing the pushing? Is it letter A? Is the force of friction here 0? Or is it letter B greater than 275 newtons? Or is it letter C equal to 275 newtons? Or could it be that there is a very, very negligible amount of force of friction that is in letter D? Alright, so what is the best answer? Okay, so what, which law, which among the three laws, the first law, second law, or the third law, will explain this situation? Okay, for the car not to be able to move, okay, despite the fact that there are forces acting on the car, all right, in short, the car stays in equilibrium. And when we talk about equilibrium, okay, a body that remains at rest, okay, it should be the first law that we have to use in explaining why the car won't move. So, according to the first law, the reason why the car doesn't move, okay, is that these two forces, capital F and small f, in fact, they do cancel each other. In short, the F net must be 0. So if F net equals 0, okay, the forward force, capital F, exerted by the man, which is 275 newtons, is just balanced by the force of friction exerted to the left. In short, our answer to this question is, alright, so there you have there the emphasis is that the F net must be 0. And therefore, the two forces acting on the car, the applied force and the force of static friction, must be equal. Alright? Therefore, our answer to number 8 is letter C. Question number 9. A parachutist is descending vertically at a constant speed of 6 meters per second. If small w is the force of gravity and small f is the force of air resistance on him, which of the following is true? Letter A, W is equal to F. Letter B, W is greater than F. Letter C, W is less than F. Or letter D, W is equal to F and both are equal to 0. Okay? So, just like in the other problems we did earlier, let us identify the forces acting on the parachutist. Number 1, we have the downward force of gravity pulling on the parachutist downward. Okay, we label it as small w. And then we also have the force exerted by the air resistance trying to oppose the motion of the parachutist. It's directed upward. Okay, that's labeled small letter f. Now, the key word in the problem is that the parachutist is descending vertically at a constant speed of 6 meters. Sometimes we also call this the terminal velocity. In skydiving, the term terminal velocity is the velocity that is acquired by the diver whenever the force of air resistance is balanced by the force of gravity. In other words, if F is equal to W, then the diver must be in a state of what we call constant speed or a terminal velocity. At such terminal velocity, uh, the diver will be able to move down in such a way that the impact force that he's going to experience will not really be that deadly. Okay? So, this is, again, an application of Newton's first law of equilibrium. Okay? Constant speed means that the F net acting on the diver or the parachutist must be equal to 0. Okay? But why does the diver not stay at rest? Why is it that the diver will continue to move until he reaches the ground with constant speed? Alright? The reason is that after jumping from, let's say, an airplane, he must be speeding up. Okay, the force of gravity, which is equal to his weight, is not yet equalized by the air resistance. No? But as he gains speed, the air resistance also increases by as much as the square of the speed of the skydiver. That is how the air resistance is increased, okay, depending on the speed of the man or the parachutist. So, in other words, it will take a while before the diver will be able to reach what we call a safe terminal speed. So, in this problem, Since the F net is 0, the two forces acting on the porosities must be equal in magnitude but opposite in direction. In short, our answer to question number 9 must be letter A. We are down to the last question. Question number 10. An object is thrown straight up, reaches its maximum height, comes back to the same level it was thrown. Now, the question is, which of the following information on the net force acting on the object is true? Okay, we will assume that the friction is negligible. So, we represent the object as a particle. Okay, so when it is thrown upward, all right, what do you think is the force acting on the object? Of course, we have the downward force of gravity, which is labeled here as W, as in the weight of the object. All right, so as soon as this object has been released, for example, from the hand of the thrower, so it continues to move up until it reaches the maximum or the top of the height maximum. Okay? Then, at that point, is there a force of, is there any force that's still acting on the object? Of course, because there is still the force of gravity present, okay, being directed upward. Downward. It's the force of gravity downward, labeled as W, right? Then it starts to move down. When it reaches that point, there is still the force of gravity, again exerted downward, all right, on its way down. So in short, uh, in any point along the path of the object that is thrown, whether it's upward, whether it's at the peak of the height, or whether it's on its way down, okay, the force acting on the object is equal to the force of gravity or its weight. Okay, assuming there's no air resistance, then we can conclude that the force of gravity is also equal to the net force acting on the object. All right? So therefore, if we look at now the choices, here are the different or the four choices that you're going to select. All right, for letter A, here are the condition. On its way up, it says there that the F net is directed downward. At the maximum point, the F net is 0. And on its way down, the F net is directed upward. That's for letter A. For letter B, on the way down, on the way up, the F net is directed downward. Okay, at the top of the maximum height, the F net is downward. And on the way down, the F net is downward. For letter C, on the way up, the net force is directed upward. And the net force at the top of the maximum height is 0. On its way down, the F net is downward. Or should it be letter D? On the way up, the net force is upward. At the maximum height, the F net is downward. And on its way down, the F net must be downward. So since we already said earlier that the only force that constitute the net force acting on the body is the force of gravity. All right? So In short, this force of gravity or the F net at any point in the flight of the object moving up then down, force of gravity is always downward. In short, our answer to this last question is letter B. So that ends our discussion about Newton's three laws of motion. Don't forget to subscribe and hope to see you again in the next video.